Morning, everyone. So yesterday we introduced the notion of significant figures. Those were the idea of keeping around meaningful digits. The meaningful digits are all the certain ones, the ones I'm 100% confident about, but it also has one guess. The guess is always the one that's farthest most to the right. That one I could very well be wrong, but it does give me a little bit of information. We talked about assigning significant figures, especially when we're not the experimenter. Digits 1 through 9 are always important. The 0, you're going to use an arrow rule. Remember, even as the arrow cuts through the zeros, they're just identifying in terms of this significant figure. They're not significant in the sense of giving you any detail, but they are still present to make sure all your other numbers are still in the correct positions. Towards the end, we ended up with some sig fig calculations. For adding and subtracting, we lined out the decimal place. For a mixed calculation, we ended up having to follow through our rules, multiply, divide. I'm going to show you a quick example of both of those as we look towards error in today's lesson. So just as a quick little warm-up here, again, feel free to, once you have the question down, just pause the video, try it out for yourself, and then you can resume and see what you get. So let's do two questions here. First question, 1.5 times 10 to the 4 minus 2 times 10 to the 2. Let's add 3.70 times 10 to the 3. Right. So what you want to see in this question here is all of these are scientific notation. So these order of magnitudes here stick with your number. So although it does mean times and whatnot, but it's just telling me where the decimal place here ends up. This one here, our operator is actually just the plain old minus and the plain old plus. So the rule here is we're going to round to the least decimal places, right, or round to the least precise position like we mentioned previous. The hard thing here is because they're all in scientific notation, I don't really know how the decimal places are going to line up. So I'm going to show you two ways of doing this here. The first way is sort of a brute force method. Basically convert them back into standard form. 1.5 times 10 to the 4 means move the decimal place 4 over. 1, 2, 3, 4. Oh, this number here is 15,000. Do a minus with 2 times 10 to the 2, so that number here is 200, and then 3.70 times 10 to the 3, so that means 3,700 there. Right. Normally when you're doing this, you wouldn't do a minus and a plus directly, but again, I'm going to have my calculator so you can just punch it in fairly easily. So that's the brute force method. 15,000, I'm going to minus off of 200, add a 3,700, and I get 18,500. So by doing the brute force, I just line out the decimal places here, and at least all the digits will add up correctly. And now when I just use the lens of significant figures here, because I know these ones here would have been measurements, I do want to follow the rule of rounding to the least decimal places. So 1.5 is guessed at that 5 there. The 200 only actually has one significant number, and that's guessed at the 2. The last one here with 3.70, that one's actually guessed at that 10's position there. Remember, in scientific notation, all base numbers here are important. Which guess is the worst? In this case here, I would say, well, it's 1,000. That's off. So I want to round it to this position. Again, I've given you a lot of examples that these are even 5s. If this was like 501, no doubt about it, you just round it up. In this case, you're even an even 5, you round it up. So your final answer here would be 19,000. Your worksheet might ask you write your final answer in scientific notation. That's just to get you some practice. Make sure if you write in scientific notation, make sure you do it with the proper format. Especially if these powers got larger. If this had been like 10 to the 6 and one was 10 to the negative 3 and 10 to the 17, things like that, this brute force method, although it works, we're having to count a lot of zeros and the chances of you making a mistake is actually fairly higher. Are we able to do this lining up the decimal place without actually converting over to standard form? So I'm going to show you a quick technique here. What we can do here, like I said, the order of magnitudes here have been pulled out of these numbers here. If I can line up these order of magnitudes, this will effectively line up the decimal place. Now, to be sure what I'm doing here, I'm actually going to switch it from like proper scientific notation to something that's not proper anymore. But I'll show you how this works here. I have a power 4, power 2, power 3. Let's imagine converting all of them to a power 4. What would this number be if I really wanted to express it something times 10 to the 4? Well, so far it had been 200. If this becomes a bigger power, then I would actually have 0.02. You can try it out for yourself here. I gain those two powers again, so I end up with the number 200. Not correct scientific notation because the first digit is not between 1 and 9, but useful for this math here. Second conversion here, 3.70 times 10 to the 3. Again, I want to make it 10 to the 4, so I'm going to round that. Let's make it 0.370. That's incorrect scientific notation, but at least they're all 10 to the 4. Like I mentioned, you could have made everything 10 to the 3 or 10 to the 2. You just want to make match up the powers. So match up powers to line up decimal place. Just want to show you another variety of how you do this question. And in that case there, because in this case now they're all 10 to the 4, I can then say 1.5 is times 10 to the negative 4. Then I have a minus a 0.02, which is also a times 10 to the negative 4. A 0.370, which I'm going to add, 0.370, also add a 10 to the negative 4. Effectively, I factored the times 10 to the negative 4 out. The decimal places are now going to line up, right? Even though they weren't correct scientific notation. This right here would give you the 1850 like you said. And in this case here, we're going to go, well, this is unsure first decimal, second decimal, third decimal. So we're unsure the first decimal. Let's make this number here 1.9. But remember, at the final answer, it still needs to be at this position. Sorry, 10 to the positive 4, I meant, times 10 to the 4. So we've been able to line it up without necessarily brute force and actually writing out all the standard notation. We can line up the decimal place in that fashion. Just to give you some practice with the mixed calculation as well. Fortunately for us, we don't see mixed calculations very often, but you do want to be careful depending on the operation, which rule you're actually using. So let's just try out one here and just make up some numbers. 6.7, let's add a 30.59. Let's divide that part by 0.26. Let's minus off 4.0 times it by 9.02. Right? So it could be any mixed operation. The reason why we don't need to deal with mixed calculations very often, if you think about the unit conversions we've done up to this point, they've just been simply, multiply this, multiply the numbers on top, divide the numbers on the bottom. Well, that's all based on the multiply divide rule, so you just round the final answer to the lowest sig figs. Although remember, for unit conversions here, definitions are infinite significant figures, so we really usually are limited just by the starting measurement. First thing I would do in this question here is I would just type the whole thing in. Make sure you follow your BEDMAS here, 6.7 plus 30.59, do the divide 0.26. I'm going to minus off bracket, 4 times 9.02. No matter how weird my rounding gets to later on, the calculator should be numerically something like that, 107.343. Sometimes I get people getting lost through the calculation here, and they end up, because of rounding, they end up getting something that's totally not 107. Just do yourself a favor and do that part first. Let's do the operations here. 4 times 9.02, calculator gives you here 36.08. If this were the end of the question, I would have done the multiply rule. So I would have said, this has 2 sig figs, this has 3 sig figs. This one should only be sure to that 2 sig fig. It should really just be 36. I'm not actually going to round to 36 because that would be an underestimate. It would have gotten rid of this 0.8 part. Now let's do the plus part for the top. So 6.7, 30.59. I'm just going to do that part on the side here. Because the add rule is different from multiply and divide, I'm just going to do it separately. So 9 to, what's that, 37.29. Remember, for the addition subtraction rule, you line up the decimal place. This one's unsure at the first decimal place. This one's unsure at the hundredths place. I should be rounding it to 37.3. I'm not actually going to do the rounding, but I'm going to put a circle around just to show you it behaves like it's precise and guess at that first decimal place. Now you're going to notice in the next step, I'm going to take the entire number, 37.29, only precise up to that 2, divided by 0.26, and basically crunch it through the divide rule. So the quotient here, take the entire number divided by 0.26. This is where I get the 143.423 yada yada. Normally a number like 37.29 would be 4 sig figs, but based on my add rule, it was only precise up to here. We now only have 3 digits significant. The other one has 2 digits significant. So this one here should only be rounded to 2 digits significant. It should have been rounded to 140. But I know, again, I'm not done the question yet, so I'm going to keep everything else around. I'm just going to put a circle around where I'm guessing. So finally here, we get ready to do our subtraction. I'm going to take a 143.423, use that answer button in your calculator, so it recalls it completely. And what they want you to do is they want you to subtract off a 36.08, again, unrounded. But like we said earlier, this was only sure until that 6 there. We're back to doing minus, so we want to do the least decimal places. This is where the calculator should still be giving you that 107.343 number, right? No matter how weird my rounding gets, I get numerically the same value, but now I do the sig fig rules here. This is off at the tens, this is off at the ones position. So I want to round it back to the tens position, and finally it's going to be 110. You notice that was a lot of work. It isn't just so simple as just being like, oh, I have 2 sig figs, so my final answer 2 sig figs. We had to follow the particular rule for the particular math that we actually did. So make sure you get a lot of practice with that there, and we'll go from there. Today in our lesson, I want to introduce to you the notion of error. Up to this point, we've been looking at uncertainty, this sort of precision argument, this sort of how sure are you in your measuring tool? Is it easy to read? Is it not easy to read here? Error actually turns out as a totally different concept. The thing that mixes people up, however, especially let's say you're in physics here, they do refer to this one here as an experimental uncertainty. So just be careful. For us in chemistry, uncertainty meant sig figs, what we just practiced there. When we actually switch over to error, well, I'll leave the math for this stuff here in the next lesson. But today I just wanted to introduce to you what is error and how it's actually different from uncertainty, how it's different from the significant figure stuff that we just talked about. In fact, when we do error, error by definition is the difference between your measurement and the true, or sometimes we refer to it as an accepted value, if there's no real value to compare it to. You'll notice in this notion here, we're not talking precision. We're not talking how many digits am I keeping, how many am I rounding, how many are meaningful or not. This time, this is more so an accuracy argument. It's saying we were supposed to get some target value, some true number. How close to that true value did you get based on when you actually did the measurement, when you actually did the experiment? So in this case here, totally different concept, except confusingly, it actually is called an experimental uncertainty. This is where we actually come back to those 2 key terms here. In science, we have accuracy as well as precision. These are 2 different concepts, although we want both high accuracy and high precision. If you remember from your junior science classes here, to be accurate, this is what we just talked about here. This is the closeness to the true value. You were supposed to find a certain number. The closer you are to that number, the better your accuracy is. We use other synonyms like, is my measurement valid? Did I actually get what I set out to actually go for? So as an example here, let's say, again, just using the analogy of counting the students in a classroom here, let's say the true value was 28. Someone just walks by the hallway, I ask them to take a quick count, oh, how many students are in the classroom? If they are able to tell me 28, they are fully accurate. They're fully valid. It's fully exactly spot on. That's what I wanted. What if they said, oh, 25? Well, they're off. They're actually different by quite a bit. They're missing 3 students. Maybe they didn't look around the door and actually missed the side of the classroom, but they're off for whatever reason. I ask them again. Sometimes in science we like repeating measurements. They say 26. I ask them again. They say 25. I notice that all of them, they're off, right? They're not accurate. It's not a valid measurement. It's not a valid assertion of how many students are actually in the classroom. What we're doing here, however, is as we start getting repeat trials and many measurements of the exact same quantity, precision is actually a measure of the closeness between repeat trials. And that language of trials is making the same measurement multiple times. So it's like me going up to this person and saying, count the students, count the students, count the students. Every time he counts the students, that's referred to as a trial. Synonyms for precision here are my measurements reliable? Are my measurements reproducible? You notice here for precision, I'm not actually concerned with how close you are to the real value, to the true value, to the accepted one. I'm actually just saying, when you actually did it, was it a reliable way of carrying out your counting? If I count multiple times, am I getting it consistent? That's the notion of precision. So let's use this sort of dartboard analogy here. Let's say the goal of throwing darts here is to hit the bullseye. So there is a bullseye, there is a target, 28 students. That's accurate. So let's say I throw 1 dart and it lands exactly on the bullseye. I would be able to say, wow, you're really accurate. Really good dart thrower. You hit spot on. You wanted to say 28 students and you told me exactly 28 students. Fully accurate. Because precision inherently needs trials, you have to have done it multiple times. I actually don't know your precision at this point because you've only done the counting once. But if I ask you, hey, how about you throw a couple more darts? As you throw a couple more darts here, they land bullseye, they land pretty close to bullseye here, maybe not spot on. I would say, hey, it wasn't by fluke that you landed on the bullseye, like if I were throwing darts here, but you sort of reproduce that trial, you throw the dart here many times, and you actually end up consistently getting near the bullseye. That's going to be highly precise. Is it possible for me to be not accurate? So let's go low accuracy, but also highly precise. That's actually the example that I demonstrated for you here. For you to be accurate, you were supposed to hit the bullseye. The bullseye was 28 students. What if I threw a dart and I said 25 students? Whoops, I'm off. I'm inaccurate. This is an accuracy argument. I'm off. But as I throw more darts here, I get another 25, I get maybe a 26, I get another 25. You'll notice it's a very reliable measurement. You'll notice that, oh, you're also a very good dart thrower here because you're consistently getting something that's close to the mark. This is sort of the worst case in science where you do your experiment, in science you want to do it multiple times. Sometimes we say in chemistry we like doing a 5x3, 5 measurements, so 5 different samples of what you're counting, but 3 times. There's nothing magical about that 3 here, but 3 gives me some sense of consistency here. Was it by chance? Was it by fluke that the dart landed there? In this case here, I would say no, it's not by chance. In this case here, again, this is the worst case. I sort of have some confidence because every time I come in and I make a measurement, they seem to be close to each other, let alone, whoops, maybe I was standing on a slanted platform and it was always constantly knocking me off, which is why I'm not actually hitting the bullseye there. So in this case here, you'd really need to think about what are some of the problems that came into the error, and in terms of addressing how you might fix that. So that's the low accuracy, high precision case. See if you can do the corresponding dartboards here. Let's do the case here with high accuracy but low precision. And worst case, let's do low accuracy, low precision. Where would the darts land in that situation? In this case here with a highly accurate, low precise, usually, this is just a fall apart because of the analogy here, but usually you'd say, well, to be accurate, I was supposed to at least throw 1 dart on the bullseye. However, because I'm not a really good dart thrower here, it's not really reproducible. It was just by chance and by fluke that I got there. I throw another dart and I'm way off. I'm way off. I'm way off, way off. So in terms of reliability, because these were all by fluke, I have no idea which one is actually correct. Maybe I went to read a volume. Maybe it's so it's a grad cylinder and I measure the volume. Maybe it's a 10, a 12, 8 mils, 6 mils or whatever. Maybe the true value is actually 9 mils. You notice in this example, I don't actually have to have thrown a dart that actually says 9, but what this analogy is saying is somehow if you average these darts here, somehow you're landing somewhere in the middle. Just like if you average these numbers here, let's add them all up and then divide it by 4. We end up exactly spot on. Let's say the true value was also 9 milliliters, so therefore my average is spot on, so I can still conclude. Even though we don't have the consistency, the reproducibility, the reliability, we're still fairly accurate. Low accuracy, low precision, you can imagine then, if my darts here are by fluke, they're landing all over the place, even if I did this average, I'm still way off, right? In that case, they're low accuracy, low precision there. So I want to show you with this numerical example, it's possible to be, in this third case here, highly accurate, even though if I haven't thrown a dart exactly on 9, and better yet, even if I had a 9, when you look at these 5 measurements, I don't know which one is actually the true value. It's more so the average is close to the true value that makes you accurate. One other comment here is I can comment on precision. Although inherently precision is supposed to be this notion of trials, you had to have done this multiple times. Sometimes, if you think about all the uncertainty stuff that we've done so far, we've been saying, oh, this has the precision of 1 decimal place. This is a detail. This one is a good ruler, bad ruler. We've been using the terminology precision, and that's sort of a little bit of a cheat here. What we're going to do is we're going to redefine precision a little bit. Precision on a single measurement. Right? Technically, it's like throwing the 1 dart. I don't know if it was by fluke or by chance that you hit there, but the precision of just getting a single mint is given by more decimal places. The more decimal places that you have, the more precise the reading is. So for example, if I had 2 scales, so scale number A, weighing a mass here, One scale reads 52 kilograms. Scale B reads 51.98 kilograms. Even though I've only stepped on the scale once. I stepped on scale A, it said 52. I stepped on scale B, it says 51.98. I've only thrown the dart once. Technically, I have not done any trials. I haven't asked the person, step on A again, step on B again. But just looking at these numbers as being reported to me, I'd say, well, this actually has the precision of the hundredths place, so the second decimal place. And therefore, I would conclude scale B is still more precise, even though it is technically just a single measurement. Now, why do I say more decimal places? This was a question left from yesterday here. In general, it also usually corresponds to more sig figs, right? If I have more significant figures, I keep more. I don't have to round it off. More digits of meaning. Generally, more sig figs usually implies more decimal places. But let's just do a comparison here. This number here has 4 sig figs. Let's compare this to another measurement here. Let's say my scale reads 0.000002 kilograms. So it's a really fine-tuned scale here. So 0.00, that's kind of crazy precision that we get there. In this case here, if you just use the sig fig argument, you'd say, well, this has 4 sig figs. It should be high precision. This one only has 1 sig fig. Why would that be more precise? But again, because we're using the notion of decimal places, we're saying this one was unsure. We're guessing already at the second decimal place. There's no reason to keep anything thereafter and off of that. What if I actually am what if I'm actually guessing something that's way beyond? I might still argue this one here is more precise, even though it only has 1 significant figure. So just watch out for that here. Usually if you use the lens of decimal place, usually gives you the correct answer, and in general it correlates with more significant figures. Why I have it on the board here as well. In general, especially out of your conversions, things like that, sometimes out of the math it comes a fraction. Let's say I get a fraction like 1/3. You don't want to leave your work like 1/3. I want you to still write it as a decimal place, because the 1/3 here, this one here, it implies that it's exact, right? Which is not. Better yet, if I have 0.33, don't even do the repeated or anything like that. We'd actually round it to our sig figs. So use decimals to show, in this case here, to show precision. So I want you to avoid fractions that look exact and repeating decimals. I'd rather you round it, even though I know it might be off. I know sometimes people like even saying it's approximately equal. I understand that when you write a number, I understand that one of them is going to be a guess, so you can still use the equal symbol there. Right? So that's the whole notion of error. We see that it's slightly different from uncertainty here. I'm going to show you how that error is addressed here, where some sources of error in today's lesson, and tomorrow we'll come back and take a look at some of the math for error. So I'm going to end off with these 2 main types of error. You may have heard of these 2 types already. The reasons why my dart may be off the bullseye is because of these sources of error. One source of error is referred to as a random error. Random error, by definition, has an equal chance of being higher or lower due to unpredictable fluctuations. That word fluctuations just means jumping around. Due to unpredictable fluctuations in the device, in the apparatus itself, or in your interpretation, in our limitations in making the measurement. So let's do an example here. Let's go back to my grad cylinder. Let's say this mark here says 10. I fill it up with a little bit of water. Water does form this meniscus shape. So meniscus is the name of this curve structure. Basically, water adheres. It basically climbs up the walls. We're always best to read the bottom of the meniscus. Let's say I asked a few people around the room, and I asked a couple times how much water is in here. So I would get some values. I get, I think there's 3 mils, 3 mils, 4 mils, 2 mils, 5 mils, 3 mils, right? I'm not surprised that even though we're looking at the same graduate cylinder, I'm not surprised to have a little bit of variation, a little bit jumping around, because I know this is not a great grad cylinder. So depending on how good you are at estimating, I have equal chance sometimes being on the high side, like on the 5s, sometimes on the low side being like a 1. If I were given all these numbers, I'd probably take an average. I'd say, well, it looks like the 3 is coming up very commonly. And I'd say the measurement inside is I have 3 milliliters, but because I may be wrong, up or down evenly, I'm going to then have a plus or minus. I don't want to capture the extremes here. Maybe I'll say plus or minus 2 milliliters. And in chemistry, you are allowed to drop this first unit here, so you can just equally well write it. Well, I'm guessing the volume inside the grad cylinder is 3 plus or minus 2. I might be as wrong as 5 milliliters, 3 plus 2, or I might be as wrong as 3 minus 2, 1 milliliter. That's giving me a sense of accuracy. That's giving me how close to the true value that I'm actually going to be. Tomorrow, we're going to call this an absolute error and do a bunch of math with it and propagating. In this case here, unfortunately, because these are unpredictable and these are just random fluctuations, you can never eliminate. Okay? Can never eliminate. So I don't want you to ever say in a lab, there are no random errors in this experiment. There's always random error, right? In this case here, it wasn't fluctuation of the device was just sitting there. It's a fluctuation in our interpretation. Some of us estimate too high, some of us estimate too low. So what we're going to do here is we're going to try to just limit it. I can't get rid of it completely, can never eliminate, but minimize. How can I lessen the impact of it? In this case here, I've already alluded to it here. Minimize with repeat trials. Do that measurement here more times. As you get more numbers, as you ask more people, the chances of the ones that are way off on the high side, way off on the low side will sort of be averaged out. So far I've asked 9 people. What if I ask a bunch more people? They start saying 3, 3, 4, 3, 3, 3, 3, 3. I'm actually building my confidence that it's probably about 3. So I might even be able to lessen my error bar the more times that I actually ask people. Sometimes your error bars don't quite hit the extremes, but usually they throw out a number like 95%, 97% confident. We want to leave yourself a big enough error bar to capture some of these extremes here. So those are random errors here. What you're going to see on all of our labs is they're going to always ask you, in this lab, where are some places that random error showed up? The second type of error is called the systematic error. You're going to give me some specific examples of both of these errors, and you're going to talk about how you might address them, how you might actually lessen their impact. For systematic error, we'll end off with this. A systematic error here is a deviation, so it's a leaning, a deviation in one direction. So this is different from earlier. It's not sometimes high, sometimes low. It skews your values either all too big or all too small. And these ones here are usually, keyword here is predetermined. Usually something was wrong with your apparatus, so predetermined by the apparatus, by the equipment itself, or it could even be your procedure. Something was off in your reading. So let me give you examples of this one here. I mentioned water ends up forming this meniscus shape. So if I accidentally, if I reading top of meniscus, that's not the right procedure here. If I've been always reading the tops, you'll notice every time I guessed it, whichever number I said, it's always going to be an overestimate because I was supposed to actually read the bottom. So you're not supposed to read the top of the meniscus. The apparatus itself, it could be not calibrated. That's could be as simple as taking an electronic balance here. At first, when it says grams, when nothing's on it, it should say 0. Sometimes based on whoever was using it last, sometimes it may be something off 0. There's usually a 0 button, or there's usually a calibrate. They sometimes actually call it a tare button as well, T-A-R-E. And those ones there, you basically press calibrate to basically reset the scale to 0 so that you can put your actual masses on top of it. If we get a chance to actually take a look at a diagram scale is like a teeter-totter. It has one mark that rocks back and forth. It has a mark that doesn't move. To be calibrated, these lines here should be directly across from each other. If we are not careful, and if the lever arm is actually not calibrated to begin with, either all my values would be too big or all my values would be too small. There's usually a tiny little metal knob that's on the end here that you can twist to steady this calibration here. Although each diagram scale has a set balance pan, you don't want to accidentally mix and match those. So these are usually predetermined. These ones here usually skew things all in one direction. I could say it could also be due to the apparatus. Silly enough here, let's say the manufacturer came back to you and said, I know you bought a 10 milliliter grad cylinder, but I really meant to say this is 100 milliliters. We'd never order from this company again, right? 10 and 100, that's very different. But you see that if the true value was actually 100, where I was guessing things as to be 2 and 3 and whatever, I was actually supposed to be saying 20, 30, 40, 50. Those would have skewed all my values, in this case here, all too small. And no matter how many trials that you do, I wouldn't know unless I tested it against another grad cylinder, unless I did another experiment to figure out, is this really 10 or is this actually 100 milliliters? I would never know that all my values are off. So that's one good way of identifying a systematic error. In this case here, we cannot minimize with repeat trials. You can do the experiment as many times as you want, but if I didn't know my procedure was off, my equipment was off, right, I would never know. So in this case here, in general, I'm just going to say but by redesigning the experiment. And the reason why I have to leave that fairly generic right now is because it depends on what the problem was. If you were reading the top of the meniscus and you weren't supposed to, it can be a simple reminder, oh, hey, start reading the bottom of the meniscus. If it wasn't calibrated, oh, just press the tear button. In general, yes, using better equipment, more precise equipment would be a nice example, but that's usually a cop-out. I'd usually rather you give me some thought of not just use better equipment to fix your errors, but tell me what was specifically wrong in this experiment and how you might go about addressing it. So as we look at some labs here, you get some examples of that. At least make sure you know these two main types of errors. Make sure you know errors are going to end up as a plus or minus bit. And then tomorrow we're going to come back and take a look at propagating errors, especially as we start doing math through calculations, what happens to these plus or minuses throughout. So keep working your way through the worksheets and let me know if you have any questions. Thanks, guys.